Hi, I'm Wonipak from Korea University. We propose Eigencontours, novel contour descriptors based on low-rank approximation. In our work, we aim to design contour descriptors to represent object contours compactly and faithfully in many applications. However, it is challenging to design contour descriptors because of the diversity and complexity of object contours. In related work, there are many approaches. First, a shape signature is a one-dimensional function derived from boundary coordinates. And structural analysis divides an object boundary into segments and approximates each segment. In spectral analysis, boundary coordinates are transformed to spectral domains such as Fourier domain. But they fail to reconstruct object boundary faithfully. We propose the notion of eigencontours, data-driven contour descriptors based on low-rank approximation of SVD. The eigencontours represent object boundaries more effectively than existing contour descriptors in instance segmentation. We perform contour matrix construction and eigencontour construction. Then we can represent the object contours faithfully. First, we consider trade-off between accuracy and simplicity, so adopt the stochastic assumption of object shapes. We find inner center and describe a boundary using polar coordinates. The angular coordinates theta are sampled uniformly, so only the radial coordinates are recorded to represent the contour vector R. We aim to exploit structural relationships in all objects of training dataset, so we adopt data-driven approach. First, we compose a contour matrix A from L-star convex contours. Second, we perform singular value decomposition of the matrix A and perform low-rank approximation. Finally, we determine the first m left singular vectors u1 to um as eigencontours. Then, we can represent an object boundary by a linear combination of m eigencontours. Figure shows rank for approximation. In this part, we show image examples of rank m approximation. As m gets larger, the rank m approximations get closer to the star convex contour. The rank 20 approximations can represent object boundaries faithfully, almost identical to the 360-dimensional contours. This shows the eigencontours outperform conventional algorithms at every dimension m. The proposed algorithm achieved f-score higher than 0.85 at dimension 20, while the conventional ones need approximately double the dimension to get a similar score. Figure compares object boundaries at the same dimension m. Mask failed to reconstruct curved parts, and ESA-seg allows complicated parts. In contrast, the eigencontours represent object boundaries more accurately. Moreover, we apply eigencontours to instance segmentation. We reformulate pixelized classification as the regression of m-dimensional vector efficiently. Table shows the proposed algorithm is better instance segmentation results than existing contour descriptors. Figure shows instance segmentation results on the COCO dataset. There is a companion paper about open curves eigenlengths. Thank you for listening.